Hi, I'm Caleb Hill, and this is my path towards data science. This recording is actually going to be a little bit faster, hopefully. I don't have a lot of time this weekend, it being Memorial Day weekend. We've got a lot going on, so just going to really quickly go over a couple things from the week. Um, First, this week I've been trying to figure out Python environments and the internal structures of kind of how Python works overall, and that's led to deleting and then reinstalling Python in a couple of different ways and trying to figure all that out. And in the midst of that, I actually wasn't able to get the IPython Jupyter kernel to work properly in Atom after going back and forth with all those things. Um, so I'll be doing everything in PyCharm for now, just to kind of move things forward with something I'm comfortable with. Um, that being said, this last week, that was where most of my focus went outside of work. And then during work, I had the opportunity to prep for a hypothesis testing presentation that I'll be doing in the next couple of weeks at work. And I'm specifically going to be talking about two sample t-tests. Um, but in order to really understand two sample t-tests, you kind of have to understand one sample t-tests. Um, so I've been kind of walking through both of those, trying to make sure I understand them, and kind of prep an example or two. And the example that I prepped for today's video is a little bit different than the one I'll actually do, but um, it's been a year, over a year since I graduated in statistics, and I haven't done as much statistical analysis in this kind of formal way, um, and I probably should use this more in my work. So I'm just going to kind of walk through this particular example. Hopefully, it makes sense, and we'll go from there. So with this example, I'm going to go ahead and use matplotlib for plotting purposes, scipy for statistical purposes, and numpy uh, for some of those statistical purposes, and just what it can do. Um, so in this example, we want to know if data scientists have a higher IQ than the general population. The way that IQ is designed is to have a mean IQ score of 100 for the whole population. So we'll be basing uh, everything off of a mean IQ of 100 for the total population. With that being said, um, I've got some fake data of data science IQs, data scientist IQs, and I'll be pulling a couple of samples from those things along the way as we go. So, um, a hypothesis test essentially is where we're going to break down into to two hypotheses. In a one sample t-test, we're going to say um, the null hypothesis is that the mean IQ of the population of this general public is the same as the mean population IQ of data scientists. So they would both be 100. And that's where we're going to base everything off of. We're going to assume that that is the truth, and then we're going to see what happens with the statistics. Um, so the alternative hypothesis is that the mean for the data scientists is bigger than the mean for the general population. Um, so with that being said, let's go ahead and jump in and grab these samples here. So I've got again these loaded up. Um, So we've got four IQs for data scientists. And we're going to go ahead and show you what that looks like in a histogram here. So you can see a couple below that population mean and a couple that are pretty above the population mean. So we're going to go ahead and grab the length of that, which is going to be 4. And I'm going to be plugging these things, kind of walking you through the basics of the math. I'm not going to formally, derive these equations or anything, but you should be able to follow along with these equations as I'm doing them. Um, so first thing we're going to do is we're going to grab the mean, which I will say is x bar, of this sample, which is 114. And that's great. We're going to grab the standard deviation of the sample, which is about 25, 26. And I have this DDOF equals 1. It's the delta degrees of freedom. Essentially all that's doing is saying, hey, I want the sample standard deviation, not the population standard deviation. And I'm not going to get into the difference between the two of those, but we want to use a sample standard deviation. And then we're going to grab the difference between the x bar and the mean IQ. Whoops, I didn't get the mean IQ here. We'll go grab that real fast. There we go. Okay, now we can keep going. So the difference is, again, just 14.6 minus 100. And that's what we really care about, is the difference between the two, between the actual mean of the population and the mean of our sample. Because we don't know the real mean, the actual mean of the data scientist group without taking the mean of every data scientist that exists, which we can't do. So moving forward here, we're going to grab the standard error, and essentially what this is going to tell us is based on the standard deviation of our population, or not of our population, but of our sample, and the number of samples that we took, what is going to be the size of a standard deviation in the t-distribution that we'll be using. And this will come into play in just a minute. But essentially you can kind of think of this as almost replacing the sample, replacing the standard deviation that we got. And I'll explain how that kind of comes into play in just a minute. And then the t statistic here, this is going to be the difference divided by the standard error. So if you think about what that means, essentially this is the number of standard deviations in our t-distribution that we are away from the mean. So we are 1.13 standard deviations above what the population mean is. Okay, and then we're going to grab degrees of freedom. This is just whatever our sample size is, n minus 1. And finally, we're going to get a p-value based on that t-statistic and the degrees of freedom. And that p-value is going to be 17%. So with that being said, if we were using a 0.05 as our alpha value, we would not reject the null hypothesis in this case, because that p-value is pretty small. And there's a whole other way of doing this, but we can also use this SciPy stats function, and it literally does everything for us without having to do the math, but I thought I'd walk through the math because I think that's really helpful. Okay, so with that being said, I'm going to go ahead and plot what exactly this means. So you see this figure here. This is our t distribution that I was talking about. So essentially, like I said at the beginning, we're assuming that the mean value is 100, that they're equal, that the mean for the population, the whole population, and the mean for data scientists is the same. So, assuming that that's the case and that's true, um, and using the standard error that we calculated, we get this t distribution. Based on the 3 degrees of freedom. And essentially, a t distribution is the same thing, not the same thing, but similar to a normal distribution, but generally wider than a normal distribution. Um, and it starts to become more normal as the degrees of freedom approaches infinity, right? So, with that being said, this red area over here would be all of the possible mean values that we could get uh, that are above the mean that we got, which was 114, I think. Um, so if I took a, every possible sample from this t distribution, right, from the population, about 17% of those samples of 4 would be ab- above or equal to what we got with our mean. So that's not super convincing uh, that to say that they're, we should say that the data scientists are bigger. Um, so we're going to go ahead and do this whole thing again, except this time we're going to grab a different sample size of 100. So if I go ahead and run everything again, show you here, just the power of having a bigger sample. Um, so we have all of our samples there. And just to show you what the histogram looks like, all right, cool. We have more data to work with. It's definitely looking like it's further to this like 120, 130 area than the 100 area, but we'll see if the statistics are enough to convince us. So n is 100, x bar is about 120, so that's really nice to know. Standard deviation is about 20. Okay, cool. Not too different than what we got before. Um, okay, the difference is just that. Standard error. Now this is where the trick comes in. The standard error plays a big role here. So I think last time the standard error was pretty big. It was like 19, I think, or so. Now it's 2. That makes a big difference, and you'll see that come into play. So our t statistic here, how far away in standard deviations in the t distribution? We are 10 distributions above. That is a big, big, big difference. And you'll see that again in the p-value here is going to be very small, very, very, very small. Basically 0, right? And so I'll show you what that ultimately ends up looking like. Actually, I don't even know if you'll be able to see how far away that is. Um, but again, you can kind of see those same results with this. There we go. So if this is our t distribution, this is how far away we are from that. Like so far away. And if you think about how this decays down, this is this is essentially 0, right? Um, and so essentially again what we're saying here is we're saying what is the probability given that I am taking every possible uh, sample of 100, okay? What is the probability out of all of those possibilities that my sample mean was bigger or equal to that 120-ish area? And the probability is so, so, so small that we then can say, hey, the data scientists they have a their average IQ is significantly bigger than the average IQ of the general population. So um, that's kind of the whole gist of everything here. That's kind of a one sample TA test. Hopefully that makes sense. Again, I've got to present on this at work, and I thought it'd be fun to kind of share this with everybody. Let me know what you think in the comments below, and we look forward to seeing you guys next time.